Hello again. This slideshow is going to be longer than the last one. Hopefully, I'll try not to drone on as much as I did the first time, but we'll see how this goes. So, Chapter 3. Here are the learning objectives. Feel free to read them. I'm not going to read them for you, just waste time. Okay, today we're going to talk more about atoms and the periodic table. Electrolyte. Electrolyte is something that conducts electricity when you put it in water. Well, molten or water. So salt. Salt is electrolyte. You throw salt in water, and water will then conduct electricity. Pure water does not conduct electricity that well, but salt water conducts electricity pretty well. So that's when you see it has electrolytes. Besides what plants crave, it is also what they put in some sports drinks to replace some minerals. And minerals, well, they're elements that we sweat out, sodium, potassium mostly. There are some non-electrolytes, so sugar is a non-electrolyte. That does not make water more conductive electricity. Electrodes, these are what carry electronic currents, electrical current. So electrolysis, this is, well, electrolysis of water. This is when we separate things out by their electronic field. So the anode is the well, okay. In a battery, electronic source, the anode is a source of negative charge, a cathode is a source of positive charge, but in this case, the way it's drawn is that the anode is becoming, this is kind of drawn in a strange way. The cathode actually should have the negative signs going towards it, but hey, I'll go with the picture, sure. Um, Ions, so an atom by definition is neutral. I'm using the air quotes here, and an ion is a air quote charged atom. So and you do this by electrons. So an anion is a negative ion. It's taken by adding more electrons to an element or a molecule. And a cation is a positive ion that has electrons ripped off. If you have trouble remembering which one is anion is negative and cation is positive, think of the T in cation as being positive, okay? The T is the plus sign. So let's talk about some experiments, how we figure this out. Joseph Thomson looked at the charge to mass ratios, discovered the electron using cathode rays. And we'll talk about soon, cathode rays generate X-rays. So that's one scary thing. Some of these experiments did generate X-rays, surprisingly. So cathode ray tubes. This is also, you can see it has the radioactive symbol in it because you're making X-rays. This is the old school TVs. Now we have flat screen TVs that do not have cathode rays in them, but cathode ray tubes used to be used for television sets. Goldstein observed positive rays using a perforated cathode. And Milken, with his charged oil droplets, observed the charged electrons. So doing that made oil droplets and had different charges on them, so it could figure out what the charge of an electron was using that. And then Roentgen discovered X-rays using a cathode ray tube. You shoot cathode rays towards a block of metal, typically aluminum or copper, and that's still how we do it today. Discovered X-rays, and then you can make X-rays of people. And this is nice because it images where your bones are, and you can tell if something was broken or not. So you can see a broken finger here being healed with that. Of course, X-rays are dangerous. They're ionizing radiation. And then Marie and Pierre Curie, they discovered radioactivity. And Marie Curie, she is an amazing person. She's passed away now, but 2 Nobel Prizes to her. Nobel Prize is the highest honor you can bestow upon a scientist. And her husband there, Pierre, he unfortunately died. They discovered radium, and they used to carry it around in their pockets and show, like, hey, this is radium, look at this. And it glows. It has a light green, I've never seen it, but it has a light green kind of glow to it. And kind of a cool parlor trick. Of course, they kept on getting sores in their around their hips, and that's from the radioactivity. And Pierre got hit by a cart, and he was weakened from radiation sickness, so he died. But Marie carried on. She had a daughter, and she got a Nobel Prize too. So lots. I don't know what happened to their family since then, but they're good scientists. So let's talk about the different types of radioactivity. There's alpha, gamma, and alpha, beta, gamma. Alpha rays, they will be deflected towards an anode, the negative end. Beta particles will be deflected towards the cathode, the positive side, and gamma rays are not affected at all. So there's three types of radioactivity. Alpha particles, they're kind of heavy. Let's see here. They're heavy. They outside the body they don't cause very much damage. Inside they can cause a lot of damage. Beta light. They're negative electrons. Alpha particles a helium nucleus, two protons, two neutrons, and a gamma particle is just a high energy photon. We'll talk about these a little bit more later in a different chapter. Uh, Rutherford's gold experiment. I kind of like this experiment. It shows the nature of the way science is partaken and how science goes in grad school. If you go to grad school, which I highly recommend, but man, being a grad student is difficult endeavor. You have very few rights. Rutherford. So at this point in time, we had Dalton's atomic theory, where atoms were these solid spheres that were indistinguishable, and then we then talked about the Millikan and the the oil drop experiment. He came up with a model called the plum pudding model. Um, a better, for a more colloquial example, would be like the blueberry muffin uh, model. So the idea was the plum pudding model. The atom was a big sphere of positive charge, and you had these electrons that were dancing around in this big sphere of positive charge. Then you had Dalton, like I said, where atoms are small, indistinguishable spheres. Uh, Rutherford said, "Hey, you know what? I'm going to solve this problem. I can tell you which one's right. I'm going to get an alpha source, and I'm going. They're really heavy, and I'm going to shoot these alpha particles towards a really thin sheet of gold. And if Rutherford is, I'm sorry, if Dalton is right, none of them will go through. And if Millikan is right, they'll all go through. And then I will prove which one is right and wrong, and then we'll have a big celebration." So he devised this experiment, and I remember this because I was learning about this when I was a grad student, and I was studying nuclear physics, and basically the story goes, he had the grad student is the one that did this experiment. So Rutherford was doing very professorly things like smoking his pipe and drinking coffee and that kind of thing, and the grad student, he was stuck in the lab, and it was dark, and if you had zinc sulfide, when that gets struck by radiation, it has a bright flash. And so Rutherford gave the grad student one of those clickers, like if you go into a club and someone, or like Costco, or someone sitting there, click click, the person coming in, gave the student one of that, and the student went down and in the dark and sat there for an hour or some period of time, click 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 for the number of times that he saw the light come this way, and then moved down a little bit, click click click, and moved down. And what the grad student found out was that, I don't know who the grad student was, it's lost to history. I'm sure we could figure it out, but that most of the radiation just went right through, but some of it was deflected. And then so the grad student took all the data, compiled it, gave it to Rutherford, and he was like, "This is wrong. You go do it again." And because it's kind of showing both. It's proving both theories, and one has to be right, one has to be wrong. Atoms either have to be solid or completely uh, completely. It's kind of, well, the fluffy with like the plum pudding model. Or the blueberry muffin model, if you will. So the grad student did it again and got the same result, and gave it to Rutherford and said, "Here you go, boss. Rutherford's like, nope, nope, it's still not right. And the grad student's like, hey, look, I've been doing this for weeks, and you've been smoking your pipe and drinking your coffee and attending lectures, and I'm the one in the dark here doing this. You want to go do it yourself? I mean, I'm done doing this kind of thing. I mean, I'm paraphrasing that, but Rutherford said, maybe the grad student is right. Maybe I should think about this while I'm smoking my pipe and drinking my coffee. And this is what he came up with. And the idea was is that the atom is mostly empty space, which is not entirely true. But it's not very massive space. An electron does fill that space, but it's not very massive. But then there's this really, really dense center, and that's the nucleus. So Rutherford had this idea of a nuclear atom where you have most of the mass of the atom is in this really dense region called the nucleus, and the rest of it is just kind of thin, empty space. And that's the reason why most of the particles just rush right through, but when it hits the center, this ultramassive particle gets deflected. And this is not necessarily Rutherford, but come with this more. So these are the subatomic particles. So sub means less than, atomic, atom. So less than an atom particle. So like a sprinkle is a sub donut particle, right? You can take a sprinkle off a donut. You can take these out of atoms. You can take protons, neutrons, and electrons out of atoms. So they're less than atom particles, subatomic particles. And proton has a relative charge of +1. It's +1, 1.6 times 10 to the minus 19 coulombs. An electron is minus 1.6 times 10 to the minus 19 coulombs. Electrons have a very small mass, about 1/2000th of that of a proton or neutron. Actually, a neutron is slightly more massive than a proton by about an electron's mass. And a neutron will turn into a proton and an electron. So if left alone or in certain conditions called beta decay. But we're given the relative mass of proton and neutron to be about the same. And protons and neutrons have different masses and different elements. And that depends on their environment. So it does change. And protons and neutrons are found primarily in the nucleus of the atom, exclusively in the nucleus of atoms. And that electrons has some density in the nucleus, but it's mostly outside the nucleus. So electrons are found in the nucleus of atom, but not to an appreciable amount. And of all that, it's the lower orbital electrons. The 1s electron spends more time in the nucleus than the others. It's mostly outside, though. So you can say it's outside the nucleus. But one of the reasons why I hope you listen to me talk is I can talk about things outside the book. So, okay, atomic structure for atoms. The number of protons defines the element, defines the atomic number. So hydrogen will always have one proton, helium will always have two, that defines the element. The mass number is the number of protons, the number of neutrons in the nucleus of that nucleotide, that specific element. So isotopes have the same number of protons but different number of neutrons, and the only element that we name the isotopes is hydrogen. We have protium, deuterium, and tritium. So protium is what we usually call hydrogen. Deuterium is heavy hydrogen or has one proton, one neutron, and tritium has one proton and two neutrons. And tritium is radioactive. So nuclear symbol, X here, we usually don't use X because Z, the atomic number, is the number of protons, and A as a mass number when we write out the symbols when we talk about nucleotides, specific isotopes of an element. And okay, so we're going to change a little bit of topics and talk about the Bohr model. Bohr model talks about the orbits of electrons as shells. So Bohr said that atoms are like ogres, or like onions, they're layered. And the Bohr model talks about the layers of the different atoms with that. And the flame tests go from the electrons jumping up the different levels. So lithium, it's hard to see in this screen, but lithium is a hot pink color. Sodium is, here it looks really orange, almost more yellow. There, potassium is a very light lavender color. Calcium is a brick red kind of color to my eyes, and strontium is a reddish color. It looks more pink in this one, but it's more red, and at least to my eyes. And let's talk about different types of spectra. Continuous spectra is so when you have white light go through a mirror, it's going to produce all colors. And we ourselves as humans, we really only see three colors: red, blue, and green. And so like the color orange to us is just the different, and the different colors are just different relative amounts of those signals going to our brain, and we interpret those relative signals from our eyes as colors. But everything else, like a spectrometer can see the differences between them, between I mean a wave like a nanometer distant difference, for instance, where we humans not so much. Okay, so we have continuous spectra here. Look at this slide here. Continuous spectrum. This is white light, and then we have line spectra here. So each element here, so you see cadmium, strontium, they have different. Well, there's a color. Like if you come up here, so we have sodium. Well, sodium is pretty solid there. It looks like calcium. You see calcium here, third from the bottom, Ca. You have some red, you have some orange, you have some blue. And our eyes, though, when we see calcium, we see it as a blending of them. But taking a prism, we can break apart the light and we can see the line spectrum here. And these line spectra, these are also like fingerprints. So meaning they're unique to each element. So we can tell what elements are in things by this. And this is, so there's a technique called atomic absorption. So if you ever go to the hospital because of heart palpitations, I never have, but I have had students that do this and they talk to me about it because it's a shake. It sounds like a scary experience. And I had one student, they injected her with potassium chloride, and then she passed out and got rid of her palpitations right away. How'd they figure out that she needed potassium? Well, they took her blood and they threw it in an atomic absorption machine and looked at the relative and look at the light coming out, and they could say, okay, this patient doesn't have enough potassium, so let's add potassium. So the atomic absorption is it's a flame test. It does this, and then looking at the amount, the relative abundance of the light there, you can see what elements are there. The atomic absorption cannot see carbon, oxygen, or hydrogen though, because that's in maybe not nitrogen either. If they use air, maybe they use a different purging gas, but it has to do with that's because it's uses a flame, uses a natural gas flame which has carbon and hydrogen in it and oxygen in the air to burn it. So, but you can see the elements in the atomic absorption. And if you ever hear people say outlandish things like the sun is 30% helium and 70% hydrogen, like, oh, how the heck do you know that? I haven't been to the sun, and I haven't walked on the sun. They do that by the light coming out and by using these spectra. Okay, so where do these colors come from? So let me come up with a different example. Let's say that you're having a party, like a movie party, and you have different layers. In front of you have a TV, and in front of the TV you have this nice lazy boy chair, and behind that you have a couch, and then behind that you have standing room. So if you're the first one there, what are you gonna do? You're gonna sit in the lazy boy. Why? Because you're in front of the TV. It's easy to see the TV. You can put your feet up and you can like really, really relax. Behind that, you have the couch. Like, well, you're not like laying down in the lazy boy. But, at least you get a comfy couch. And then behind that, someone's standing. You're like, all right, well, I'm here. I guess I had to stand. What happens when the lazy boy opens up? Well, someone goes up, they go to the bathroom. What happens? There's a mad rush for the lazy boy. That seat opens up. Someone goes down there. And what do you do when you sit down? You relax, like, ah. Okay, so let me compare that to what's going on here. So instead of a television, we have a nucleus. Instead of a lazy boy, we have the first quantum energy level. So the n equals 1 level. Instead of a couch, we have the n equals 2 level. Instead of standing room, we have the n equals 3 level. And you can see is that as the electrons in their shells move further and further away from the nucleus, they they have higher energy. And electrons are like people. Electrons like to be low energy. So if I told you I want you the same thing for the next 2 days, what are you gonna say? I'm like, I'll pick sleeping. That's what most people say. If I do it for 2 days, knock me out. I want to sleep. No one's gonna say, you know what? I really want to do. I want to hold 200 pounds over my head and run up and down stairs for 2 days straight. No one's gonna pick that because that's high energy, right? You want to be low energy. You're gonna pick sleeping, lying down, at very least sitting in a chair, right? You're not gonna be doing jumping jacks for 2 days straight. So electrons are like people; they like to be low energy, and so uh, when they find that, they'll tend to be towards low energy. And if something happens, an electron leaves that comfortable state, they'll relax down. And so energy has to be conserved. When electrons lose energy, the energy has to go somewhere. The energy is released in the form of light radiation. So and depending on the steps, we haven't learned this yet about the electromagnetic spectrum, but the different levels. So the bigger steps have higher energy, lower frequency light. The small steps have lower energy, higher. Uh, I'm sorry, low energy, lower frequency, higher wavelength light. So this is the spectrum. This image here says energy level. This is for the hydrogen atom. And if you take astronomy or physics classes, you might see this again. The first series, the ultraviolet wavelength, this is also known as the Lyman series, and the visible light is known as the Balmer series. The Lyman series goes to the n equals 1 state. The Balmer goes to the n equals 2 state. So, but hopefully I've explained this to you. Much of this is above and beyond the course, but I wanted to talk about this and explain the slides. So as you're reading the book and seeing if I know I gloss over some of these stuff, but I wanted to give you a little bit more of an explanation here. And a quantum, what is a quantum? It's a set thing. It uses discrete mathematics. So if you have continuous mathematics there's something between 1 and 2. It's 1.5, and there's an infinite number of points between 1 and 2, right? So, but with quantum mechanics, there is nothing between 1 and 2. It's discrete. You have 1, 2, 3, 4. You have whole numbers. So you can have 1 electron, 2 electrons, 3 electrons. You cannot have 2.5 electrons, and you cannot have 2.672 electrons. You have to have whole numbers, and that's how quantum mechanics works. And this comes from the fact that matter has structure. Space-time itself has structure. So imagine if this wasn't true. Everything would tend to be low to the lowest energy level, and everyone just sink down and have no structure. The fact that we have these different quantum levels gives matter structure, and because of that, there are certain things that gives it structure, so that way matter cannot occupy the same space at the same time. So otherwise, right, I mean, when we clap our hands together, they would just pass through one another. They wouldn't resist and clap. You wouldn't, when you rub your hands together, you form friction. It is because you're taking the electrons and those are occupying space and it's rubbing against the other electrons and you're trying to force them together and they're resisting each other so that motion energy turns into heat. That's what friction is. Okay, so moving on though, quantum mechanics, hopefully I've explained a little bit. We'll go a little bit more explanation with this. Okay, so the lowest energy state is called the ground state, and a high energy state is the excited state. And when things relax, it emits a photon, so which I have described there in the picture. If you want to back up the video and listen to me again. Okay. And this is the Bohr model with the shells, and the shells we'll build up to are the periods in the periodic table. But the energy level system is called shells. And we have the quantum mechanical model of the atom. So this is the most contemporary model. This is built off of all of it. Recently, Rutherford was the recent one. Because Rutherford said that there's a nucleus and an empty space. We're saying it's not empty space, but we have electrons that behave in a quantum mechanical fashion. And there are lots of courses on quantum mechanics, many more than this one, but we're just going to do a very, very brief mention of the quantum mechanical model. And So here are some of the quantum mechanical model. I'm probably going so quickly over this. If you want to come and talk to me, go more, or better yet, take my Chemistry 161 class. I will go over this in much greater detail. So we have the principal energy levels. These are the N in the quantum mechanical model. This is the principal quantum mechanical model. We have the subshells, and the principal is divided. It's actually N minus one sublevels. So, I should say that I guess it is N sublevel, but the number L, the quantum mechanical number L, it's n minus one, and the orbitals. This is left over from the Bohr model. This is the region that we tend to see the electron. It's a probability. So for the L equals one, the sublevel there. This is the s orbital. It has a spherical shape, and then we have the p orbital. So the different orbitals that we see as ground state are s, p, d, and f. Those stand for S is sharp, P is principal, D is diffuse, and F is fine. Those are spectroscopy terms. People almost never use that anymore. If you're wondering, S is not spherical, P is not perpendicular. It's sharp and principal. Okay, so and this is the 1s orbital. It looks like the 1s orbital. And here are the different p orbitals, and they have different orientations among here. And if you combine these orbitals together, the atom is more or less spherical. So and the s orbital, the 1s orbital is going to be shrunk towards the nucleus of the atom. Okay. And then when we build up, and I I don't want you to go out and memorize this stuff. I mean, I know I've been talking, you're like, oh crap, what do I have to know? I don't believe in much memorization. So I mean, some things maybe you should memorize, like an electron is negatively charged. Yeah, that's something you probably have to memorize. But I mean, how the order, the building up order of the, no, you don't have to memorize any of this. But let me go over some of it. The electron configuration, you have the principal number, that's the number one, and then the s, this is the angular momentum quantum number. L equals 0, that's an s orbital. L equals 1, that's a p. L equals 2, that's a d. L equals 3, that's an f orbital. And then the exponent on that orbital tells you the number of electrons in that subshell. Okay, so when you look at nitrogen here, you have 1s squared, 2s squared, 2p3, and that means that you have the first main shell. There's 2 electrons in the 1s orbital, and the 2s electrons, there's two electrons in that orbital, and then there's 3p electrons in the 2p orbitals. And here is the order filling chart. I don't really like this one. I guess I could kind of memorize that. I can tell from the periodic table. Much of this is above and beyond this class. And this is only for electrons that, or atoms that have more than one electron. If you have one electron only, that's known as a hydrogen or hydrogen-like atom, and then the electron energies are known as degenerate. So here are the electron configurations. This is important for the lab class if you take it with me. But a lot of it I just kind of give to you. Again, this class is not intended to be for majors. This is for students who do not intend to go into a STEM career. This is just for people looking to get their physical science out of the way. And here we go, atomic number. So hydrogen has atomic number 1 and so on. So the atomic number is the number of protons. An atom is neutral, so the number of protons equals the number of electrons. And this here shows the configuration growing in size. Okay, and this is the second period there. Actually, no, that's the second period. This is goes on through calcium So up to part of the fourth period. Okay, so periodic table, it's very productive. It's a very productive tool of all chemistry. The columns are called groups or families, and the rows are called periods. So the periodic table is from the rows, the period of the table. Groups and families, these have very similar chemical properties. So an example of family, copper, silver, gold is the same family. You're like, well, those all look differently. Copper, silver, and gold are similar by the fact that they're very inert. So you have very reactive metals like the alkali family. We'll talk about in a little bit. Those are very reactive, but then copper, silver, gold, those are very unreactive. And the periods, there's moving across the periodic table. The properties of elements change as you move from left to right. Okay, valence. So talking more about electrons. Valence, these are outside electrons. So um, I used to live in Wisconsin, and this was in the 1990s, and like this is the grunge era. Basically, everyone wore leather jackets and faded jeans, and so I mean, you could not really tell that much about someone by seeing him or her on the street because everyone wore the same thing. And in the wintertime, really thick clothing. What I mean is, what you see is on the outside, and chemistry is very superficial. It deals with the outside electrons. What's on the inside? Hey, maybe that person with a leather jacket on had a nice, colorful uh, tie-dye T-shirt on, but you can't see the tie-dye T-shirt because it's being covered by a jacket. That's the same idea. That outside electrons kind of cover the effect of the inside or core electrons. So chemistry is very, very much so about the outside electrons. And the outside electrons are the ones that are typically lost, gained, or shared in a chemical reaction. These are typically, there's some things that involve exchange of photons that can get electrons lower, deeper down, but it's not usually the case. And the group or family have the same number of outside valence electrons. So things with one valence electrons, these are known as the alkali metals. And then beneath that, the alkali, or beneath to the right of that, second group is the alkaline earths. And then let me skip it. The far right group, and then there's the noble gases. It used to be called inert gases, but noble means unreactive. It's kind of a British term. You're like, this is the happiest day of my life. No, wait, it's the saddest day of my life. I can't tell. I'm so noble. I'm the same. That's noble. Noble is someone who doesn't react, like the proletariat, the commoner, the peasants. They are the ones that react. The nobility just are constant. And halogens, this is right before the noble gases. They're very reactive. Halogen is Greek for salt forming. So if you had alkaline earth, these are kind of some old alchemy terms. Alkaline means basic, means the opposite of acidic. So alkaline batteries means not acid battery. Your car battery is typically a lead acid battery. An alkaline battery is a battery and the inside of the solution is basic. So alkaline metals, the alchemists were like, okay, we have these metals, you throw them in water and they form alkaline solutions. We'll call them alkalis. Then we have these other things. Okay, these metals we throw in solution, so they forms alkaline solutions in water. But if I mix them together, they form precipitates. A precipitate is something that falls down to the bottom of the solution. So these are alkaline elements, but they form dirt like earth. So we're going to call them alkaline earths. That's where the term alkaline earths, you should say alkaline earth. The alkaline earths are because they're less soluble and have more precipitation reactions. So that's the alkaline earths. If you wonder where the name comes from. Okay, and metals, nonmetals, and metalloids. Metals tend to be shiny, metallic luster. They tend to conduct heat and electricity very well, and they're ductile. That means they're bendy. So that's the tend. Non-metals tend to be dull. Non-conductors, and they tend to be brittle. So this is not true for all cases. Carbon. graphite conducts electricity, and diamonds conduct heat extremely well. So, I mean, this is the general trend. They don't always work this way. And metalloids kind of do both. So, and metalloids are important because we use them as transistors. So, silicon, for instance, just sitting there does not conduct electricity. But if you put 5 volts behind it, it'll conduct electricity. And we have the not conducting as a 0, we have the conducting as a 1. So the 0, 1 binary code, that's what it's based off of. It's based off of silicon, the fact that it conducts at 5 volts and doesn't conduct at 0 volts. So that's a metalloid. And if you see silicon, it looks metallic. It's kind of weird. It's kind of it's like a crystal. It's like a metal looking crystal. And so you're like, well, this is kind of like a metal, but it's also kind of not like a metal. It's a metal-ish oid. It's a metalloid. So it's kind of like properties of both. That's a metalloid. Okay, so here's a periodic table, and divide up in the columns. So if you see here the red on the far left, it says 1A. Those all have those alkalis all have one valence outside electron. The 2A, the alkaline earths, they have 2 valence electrons. And then the F and the D block. So the F here is the second block there, and it's shown in green. The D block slightly bigger, shown in yellow, and then the P block there shown in blue. Um, those are different blocks. Typically see the A's, so you have 1A, 2A, and then it goes over to the P block for 3A on up to 8A. Those are the valence electrons, the outside electrons. Usually that's almost always the S and the P's only for the valence, and the F and the D tend to be core, or use a clothing example. Those are kind of like the undergarments. Like you're not supposed to see people's undergarments. They're supposed to be covered by their outer clothing, right? So the outer valence electrons cover the inner electrons there. And also the periodic table, we typically take the F block and we put it underneath, just because we like it to fit on it's closer to the golden ratio to make it prettier, because we like that. It's prettier and it fits on the sheet of paper better. Okay. So we're getting close to the end. Green chemistry. So we have sunlight as a very abundant source of energy, and plants take solar energy and store it as chemical potential energy via photosynthesis. And we are looking to use artificial photosynthesis to crack water into hydrogen and oxygen. And this is not typically how we generate hydrogen fuel. So hydrogen fuel is typically made one of 2 ways. It's usually made either by a process called steam reformation and that's you take steam and natural gas and you form hydrogen and carbon and or carbon dioxide and carbon monoxide. So depending on how you tweak the reaction, but you form hydrogen. That's typically how you get hydrogen, is that. Or the other thing is you can reform molecules so if you cyclize or reform molecules in a refinery, hydrogen will pop off. So hydrogen is a byproduct of that reaction. It's usable, but for most processes, it's typically done by steam reformation. But we could get it by doing artificial photosynthesis. And this is also how they breathe in nuclear subs. So a nuclear sub goes underwater for weeks, months at a time, and the sailors on the boat need to breathe. How do they breathe? Well, in the ocean, there's lots of water, so they crack water and do hydrogen oxygen. They dump the hydrogen, and they have the sailors breathe the oxygen. So really what limits the range of a nuclear sub is food. That's when they need to go to port, is because they run out of food. The nuclear fuel lasts for years, and there's all the oxygen in the ocean that you want. It's the food that brings the boat out of water. Okay, so artificial photosynthesis to crack the water into hydrogen, and we're thinking that we could use this to generate heat and or electricity with solar fuel here. So this is something we're going towards. It's hard though. I mean, wonderful thing. water is 1/9 hydrogen, 8/9 oxygen, and 1/9 hydrogen. So by mass. So you don't get a lot of hydrogen from water, and you get a lot of oxygen, which is great, right? But I mean, if you're trying to invest money and energy into something to produce usable product, it's not as efficient in that regards. And you also have to deal with although it's a fairly big amount of energy coming in, it's not as dense as like a flame is or something like that. So we're working towards this, and but as of right now, it's not very economically feasible. Uh, but we're working on it with green chemistry. Hopefully, we'll have more solutions in the future, and a copyright. So, all right, see you next class.